So, so, as usual, it's a good idea to start a new recording with some inconsequential dialogue that makes no sense for people watching on YouTube. But we should really do a previously in CS103. We were in the middle of building a Turing machine for detecting whether or not a bunch of brackets are appropriately balanced, having figured out that that was a job not achievable for regular languages, regular expressions, finite automata, right? And the whole point there is that you need to be able to remember how many brackets are open in one way or another. And that's not something you can do if the amount of memory available is fixed. And Turing's conception is of a machine with finitely many control states, but a tape which allows an arbitrarily large amount of additional memory. So you're guaranteed that only a finite amount of the tape has been used at any given time, but the tape extends infinitely in both directions and is useful for containing the input and the output and the working space that we make use of in between. And to some extent, this is a reasonably realistic model of the kind of equipment we use today, the technology by which this lecture is being transmitted. I see I have Yuri Gagarin over my shoulder. And that's the technology that put people into space. And the key thing about it is that even though we can, in principle, run out of memory, we spend our entire lives just not worrying about that. Okay, so what's the thing with Turing machines? Uh, there's a tape head, right? So there's a finite number of control states and a finite alphabet. And at any given time, the machine is in a state and can see the symbol at the current position of the tape head. And those two things and those two things alone determine which symbol is going to overwrite the thing at the tape head and which state the machine is going to transition into and whether the tape head will move one to the left, one to the right, or stay still. So that's to say, there's no kind of arbitrary action at a distance. This was invented as a way of saying that kind of apart from the arbitrary largeness of the memory, this is a notion of computation that is clearly mechanically realizable. Okay, so that was our picture. We, by convention, we're going to insist that the tape head starts at the leftmost non-blank symbol. And also by convention, we are going to declare that if the machine halts on a blank, it's saying yes. And if it halts on a non-blank, it's saying no. So that's the setup. Oh yes, and the other thing to remember is that there is one controlled state of the machine called the halting state. And if the machine enters the halting state, it stops, hence the name. But there's no guarantee that it will ever get there. So far, we've been working with automata that process one symbol at a time of a finite input. And indeed, we were able to write a guaranteed terminating program in ask that recognized whether a regular expression matched. Whereas here with Turing machines, we have no such guarantees. The machine could give us an answer, or it could just loop forever. And that's the dangerous reality of modern computing, uh, or indeed any kind of computing, that to some extent, in order to allow the flexibility to do the things we want to do, we also need the flexibility to go horribly wrong. However, let's see if we can work our way through this problem. Right, so we're interested in, I can almost, maybe I actually need to spotlight
Now
this.
it's spotlight time, I think.
Yes, because I can't read it.
I just wanted to give a few comments, Connor, if that's okay.
Sure.
So first of all, one thing to maybe keep in mind is that, so we said it's a convention that the machine, if it holds on an empty symbol, then we're happy. If it's a non-empty symbol, then it rejects the input and so on. This is one way to do it. And if you look in different textbooks, different sources, there's slightly different ways. But they will still give rise to the same notion of computation, right? So, for example, in some definitions, you have an accepting halting state and a rejecting halting state. I hope you can see that it's easy to translate between these notions, right? So if you have our convention, then you could always say, okay, if you're in this halting state, then we're just going to make one more transition and move to the accepting one or the rejecting one. And similarly, some notions of these machines don't have a stay still move. Said you could either move left, you can move right, or you can stay still. But you could also imagine that if you only have the option of moving left or moving right, then you can add one more state, which is the stay still state, and you can do it in 2 steps, right?
Yeah. Well, you might need to double the number of states because you need to remember what state you're going to go back to when you've stepped back in the other direction. But it's still going to be a finite number of states.
So the main thing I want to say is that don't take our definition here as the only possible definition. There are variations, and it doesn't really matter for what we want to do with these things, right? We want to capture what it means to compute in a general computer. And there's, just like it doesn't really matter if you're using a Mac or a PC to write your thing, it doesn't really matter what the exact definition of a Turing machine is. I mean, it has to be an exact definition to work with it, but there are variations and they are all basically the same thing.
Actually, that's one of the wider lessons we're trying to move towards, which is, spoilers, that there are lots of different ways to set up what computation consists of, and yet, despite all of these variations, nobody has in the last 100 years managed to come up with anything that can do anything different. Right. So here we were. We decided, big picture, that our strategy for detecting bracket balancing was to move the tape head rightwards until we bump into a closed bracket, and then to change direction to go back and find the opening bracket. So we're going to knock off, turn into dots, matching pairs of brackets from the inside out. So we're going to, so in particular, we're going to find all the closed brackets left to right and knock off their corresponding open brackets. So that explains the behavior in our start state. So if we see a left parenthesis or in due course a dot, we haven't found our closing parenthesis yet. So we keep going to the right and we stay in the start state. And we leave the symbol on the tape alone. That's what we're saying. If we, however, bump into our closing parenthesis, then that's great news. We overwrite it with a dot and we switch to the state where we're going left, that's the -1, and we're trying to find the match for that closing parenthesis. So we'll come back. Let's tell the match story. Right, so matching, we're perfectly happy to move past any dots we encounter. If we find an open parenthesis, then that's great news. We found the match. We overwrite it with the dot, and we move back into the start state where we're looking for another closing parenthesis moving right. If we find instead in the match state, if we find a closing parenthesis, then that means our brackets are not balanced and we should say no immediately. And that's why we leave the closing parenthesis as it is and go into the halting state by way of saying no, stay still. Meanwhile, if we find a blank, that means we have sailed away across past the input into the blank region left of the initial position of the tape head without finding an open parenthesis, which means that we've got a close that has no corresponding open. So that also means we're unhappy, which means we have to write a symbol to indicate that we're unhappy, stay still and halt. So that's the match failure. So we work our way right to the closed bracket, left to the corresponding open bracket, and then eventually in our search, in the start state, moving rightward, searching for a closing parenthesis, we instead find a blank, which means we've fallen off the right-hand end of the input. There are no more closing parentheses, but we're not done because we might have sailed past some unmatched open parentheses on our way to falling off the right-hand end of the input. So instead of just celebrating prematurely, we're going to have to scan leftward once more in the hope that all we have left is dots. So let's explain how to tidy. We have to say what to do in the tidy state for all four possibilities of symbol. And so first of all, if we see a dot, then that's good news. We might even tidy it up and overwrite it with a blank and carry on to the left and stay tidying. So that's dot, not blank.
Yes, sorry.
That's dot, not blank.
Yes.
Yes. Go left and stay tidying.
And we better clean it up and make it empty, right? Because if we left the dot, we would then in the end have something on the tape.
Yeah, well, it's not a question.
Right, it's where the head is at the tape. So
where the head is that matters. We
do
don't
have
have
some
to
choice.
tidy up the dots, but it's kind of nice. Okay, if we see either form of parenthesis, now we do believe that we're never going to see a closing parenthesis, because if there was still a closing parenthesis, then we'd have found it already. But if we see either kind of parenthesis, we are deeply unhappy We know that we're not balanced. If you see a closing parenthesis, it is because somebody violated the rule that we have to start at the leftmost non-blank symbol. Okay, but if we see either parenthesis, we're unhappy, we're going to stay still, we're going to halt. And we're going to leave the symbol as it is. So both of those are halts. Meanwhile, if we find our blank, that means we have made it all the way to left of the input. We've tidied up a load of dots. We haven't found any stray parentheses, so we're happy. So again, we are going to stay still and halt. Right. So that's
I guess in this case, it doesn't really matter where we move here, right? Because we have removed all the dots to the right of us. We know there are only blank spaces to the left of us, so the whole tape is blank at this point, right?
yes, we do hope that the whole tape is blank at this point, unless people are violating the input conditions, in which case all bets are off. And this is one of the key principles of computing, which explains why the world is in a terrible state today, which is that if you put garbage in, you're entitled only to garbage out. So we have to we operate on the basis that we are not particularly robust to people violating the conventions that we lay down.
And normally we don't mention this. We just take it as a given, right?
Yeah.
We don't have assuming people are good. We just assume people are good in this case.
Yeah, it's a strange assumption to make, isn't it? But especially these days.
It's the beauty of abstract mathematics.
Yes. Okay, shall we actually
Should we run it?
run it? Let's do it.
See if how much I can fit at the same time. But I'm going to make a tape.
Well, didn't we have
we have an example, maybe.
we have an example? We could just be messy, I think.
We want this example, yeah.
Yeah, why not?
Okay, so let's see. Can we see that? Yes.
Right. I don't know how much we can fit. You could probably push the alphabet off the top.
Yes.
In order to fit more of the definition. And also, you only need a little bit of the thing at a time. We're in the start state.
Yeah.
Okay. So we can, are we ready?
Should I walk through it?
Yeah, why don't you?
Yeah, since you explained the last bit of the program. Right, so we are in the start state. Our head is here. So we are just looking, what are we doing in the start state in this position? So we look what's on the tape. It's an opening bracket. So we follow the instructions of what's happening in the start state when we see this symbol. And it says we should write an open bracket. So we're just going to overwrite it with the same thing. And then we're going to move the head one step to the right. I guess this is going to be really messy. So a better way
just
I guess I'll just
draw a kind of bouncing. You don't need to keep drawing squares, but if you draw an arrow showing the transition.
Right, so we move on to the right, and then we move to the start state, which is where we already are, right? Okay, so then we look at what's at the head. It's another opening bracket, so we follow the instructions for opening brackets. We're going to write opening brackets, so keep the same, then move one to the right, and move to the start state, which is where we are. So then we do the thing again. We're in the start state. Now we're seeing a closing bracket. So we see what happens if we see a closing bracket. Well, we're going to write a dot. So this time, this becomes a dot. Then we're going to move 1 to the left. Then we move back to here, and then we move to the match state. Okay. So then we see what do we do in the match state? We look at the tape. It's an opening bracket. So we're going to write a dot. We are going to move 1 to the right. And we're going to move to the start state. Okay. So what we did, we found this matching pair here, right? So now we're in the start state. We see a dot. We see what we're supposed to do when we see a dot. Well, we're supposed to write the dot. Already there. Then we are moving 1 to the right. And we stay in the start state. We're in the start state. We see an open bracket. We're going to write an open bracket. And then move 1 to the right. And then stay in the start state. You see a closing bracket. That means we're going to write the dot. Then we're going to move 1 to the left. And we're going to move to the match state. Okay, we're in the match state. We see an open bracket. That means we're going to write the dot. And then we're going to move 1 to the right. And move to the start state. We're in the start state. We see a dot. That means we're going to write the dot. Move 1 to the right. And stay in the start state. We're in the start state. We see a closing bracket. We're going to write the dot. We're going to move on to the left. And move to the match state. Okay. We're in the match state. I moved on to the left, right? We're in the match state. We see a dot. That means we're going to write the dot, move on to the left, and stay in the match state. Okay, there's a dot, so we move left. It's a dot, so we move left, staying in the match state. It's a dot, so we move left, staying in the match state. And then we see an opening bracket, so we overwrite that with a dot. We move on to the right. And we stay and move to the start state. We're in the start state. We see a dot. So we write a dot. So that stays the same. Then we move on to the right. And we stay in the start state. We see a dot. So we keep moving right. 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 Then we see a blank space. So then we do something different. So we see a blank space. So we are writing a blank space. We are moving 1 to the left. And we move to the tidy state. Okay, so we are here. We see a dot in the tidy state. So we leave the dot alone and we move on to the left.
No, we wrote a blank.
Sorry, we write a blank, yes.
I'm not sure how you write a blank. I guess you can just cross it out or something.
Yeah. Okay, so we write a blank and we move on to the left. Then we see a dot, so we write a blank. And move to the left. And then we see a dot, so we write a blank. Move to the left. We see a dot, so we write a blank. And move to the left. See a dot, so we write a blank. And we move to the left. We see a dot, so we write a blank. And we move to the left. And here, we now see a blank. So we write a blank, we stay still, and we halt, right? So that means that since the head is currently at a blank space, we have accepted the input, right? And we are happy. And indeed, it was matching brackets, right? These were matching, these were matching, these were matching. And they were exactly the ones we kind of crossed out in order, right? So that's how it worked. And I hope you noticed that what I did was completely mechanical, right? There was absolutely no thinking required from my part. I just had to look things up on a table and do what the machine told me to do.
Right. And it's important. I mean, it's one of the things that Turing noticed or thought through, that the business of running a Turing machine is itself entirely mechanical. There's no magic to it. You just have to look stuff up in a table. And thinks Turing, can we put the table on the tape? In particular, we were able to write down the rules for a Turing machine in a particular encoding, and maybe the kind of data that determine the Turing machine could be encoded in such a way that they can be written on the tape. And correspondingly, Turing was able to construct a universal Turing machine. Now, what on earth's that? That's a machine which is able to simulate any other Turing machine. You write onto the tape the initial state of the machine, the setup of the machine, the initial state, the current contents of the tape. You have to do all sorts of silly encoding tricks. I mean, lots of the theory of this, which we're not going to spend time on, involves things like showing that if you have a Turing machine with two tapes, you can simulate it using a Turing machine with one tape. The kinds of things that happen are that if you can also show that if you have a Turing machine with a single-ended, which only extends to infinity rightwards, and that has it kind of stops at position 0, so kind of no infinite leftward movement, that doesn't make any difference, because I don't know, you can simulate having you can basically say the things in even positions are the rightward tape and the things in odd positions are the leftward tape, if you want to simulate a double-ended tape with a single-ended tape. And all sorts of kind of reductions like that, which enable you to make coding things up easier, right? Because that's the thing about Turing machines. They are a model of computation, but not one you'd actually want to use. They're not exactly programmer friendly. And we just about managed to cook up something that does something as simple as balancing brackets. If you want to do something as complicated as, for example, simulating the execution of an arbitrary Turing machine, then it's a bit more work. You should be glad that we don't make you program Turing machines, and don't worry, we are not going to get you to do that. Not even as a kind of masochistic practice. But yeah, the universal Turing machine, which just kind of adds some credibility to the idea that Turing machines basically are all there is. There's so the universal Turing machine, you feed it all of the data, you feed it the rules like that are on Fred's piece of paper, and you feed it the symbols that are on the start of the tape, and you feed it what the initial state is, and then the universal Turing machine is programmed to operate the rules the way Fred did. So instead of Fred being the machine following the rules on the paper. The machine does Fred's job, and the job of the paper is done. All of the bits of paper are stored on the tape. I mean, that's kind of the point of the tape, is that it can store as much as you need, but you can only access a small amount of it. You don't have infinite attention. You just have infinite potential for storage. And that gets you a universal machine with which gives you, some notion of computation. So that,
this is possible because we only had a finite number of states still, right? Which means that these tables are always going to be finite as well. There's only so many moves you can make from a given state. So that's finite, which means that we only need to put a finite piece of data on the tape to start with, right? If we had infinite number of states, then this would not work, because then you just couldn't encode it as a finite input data.
right. So the only infinite thing is the tape itself.
Also, this is how your computer works today, right? You have your program in memory and you have your data in memory, and it's all just in one place. And you load the program from memory, and then it reads some data from the same memory.
Yes, you can kind of see how von Neumann got there, really.
But the Turing machine was first, right? This
Yes.
is not so alien to us today, but this was really invented before computers were invented.
Yes, this was absolutely just dreamed up as a thought experiment.
At the time, a computer was a human that computed things. It wasn't a machine. So that's what Turing had in mind when he was thinking about computation.
Right. And the idea was that there had to be some kind of no creativity, just instructions to follow. Okay. But let's tell another bit of the story. So cut to 1900, turn of the 20th century, when everyone was still terribly optimistic about all sorts of stuff. You know, Einstein hadn't yet shoved Isaac Newton into a puddle. You know, people thought logic actually worked. And in 1900, the German mathematician David Hilbert set out a bold program. It's, you know, it's the start of a new century, and the 20th century is the century in which we are going to finish mathematics. We are going to figure out a precise definition from which all mathematical truths can be derived, and we are going to build a machine that can decide yes or no to any mathematical proposition. Now, it's clear that even if reality hadn't stopped Hilbert, his shop steward should have stopped him, because what he was trying to say was that the 20th century is the century in which mathematicians will work themselves out of a job. You know, thank goodness Hilbert's program of showing that computers could do everything has at least been disrupted until now. And how is it done? Well, it was done in various ways, but in particular, Turing showed that there was a class of mathematical problems that computers were not going to be able to solve. There was no way that this automation of mathematical decisions was ever going to work. And this is great news, folks, because it means there are things that bloody electronica can't do. But how was it done? Right. So we've got as far as the idea that there's a universal, you can construct a universal Turing machine. You feed it the rules and the initial state of the tape and all of that stuff, and you press go, and it simulates what that specific Turing machine would do, faithfully following the rules. And you're in the situation where it's just following the rules step by step. So if the Turing machine that is being simulated, if it halts, then the universal simulator will halt. And if the simulated machine loops forever, then the simulator will correctly loop forever. But the question Turing then posed was, can we build a Turing machine which will look, instead of just slavishly running the machine that is encoded as the input, can it inspect that and make an accurate prediction as to whether the machine will halt or not? So that's a perfectly sensible mathematical question. It's like, given a characterization of a Turing machine, does it halt or not? And the people who teach you classical mathematics tell you, well, it either halts or it doesn't. And to some extent, we're here to say, well, is that useful information? Is that an actual bit you can get your hands on? It's, how long is it going to take for you to find out?
So these two problems look very similar, right? So
yeah.
The first one, where we have the description of the machine, we have the initial state, and we have the input. And we know that there is this universal machine, usually called U, which produces the output of running M, and then halts if M halts. And then if M doesn't halt, then this thing will also not halt, right? That's possible. That's Turing's result. And then we have this seemingly similar thing where we have the same input, a description of a machine, we have an initial state, and we have an input. And the question is, can we find a machine which will, say, print 1 if the machine halts and 0 if the machine doesn't halt?
Yes.
It's basically the same thing.
And the point is that this halt tester itself promises to halt.
Yeah.
Yeah. So it's going to inspect a machine which might loop forever, and by reasoning about the structure and encoding of the machine, it will in finite time conclude as to whether the input computation will halt or not.
I mean, we need to ask for this extra bit because otherwise there's no use of this at all, right? I mean, there's no better than just running the original machine, and it doesn't really tell you anything. So the useful thing to ask is, can we find something that really tells you yes or no, this other machine will halt or not?
Yeah, the universal machine does the job of halting if the simulated machine halts and looping if the machine loops. But this thing is supposed to halt either way. Okay. So let's suppose we have this machine. We could call it H. Then we're going to do a classic mathematician's trick, right? We can build, if we have the H machine, right, we can build some variation on H, maybe H prime would be the thing that we would call it. H prime behaves like H, except that, so behaves like H, except at the end, if H says the input halts, H prime goes into a loop. And if H says the input loops, H prime halts. And now guess which machine we feed to H prime. That's right, we feed H prime to itself. Just check you really can. If you can build H, you can certainly build H prime because you're going to look to see when H halts, what symbol has been left on the tape, and you can very easily just add an extra state for H prime that is guaranteed to loop. You can build a loopy state that so if definitely build H prime if you can build H. Okay, but the logic then says, well, if you feed H prime to H prime in particular, then well, if H prime halts, then it loops, and if it loops, then it halts. So it's a classic variation on the theme of the liar paradox. Yeah, this sentence is false, or my favorite variation on the liar paradox is God does not believe this sentence. And the upshot of this is that H, the halting tester, cannot possibly have existed in the first place. So that means that there's a class of mathematical problem that is beyond the capacity of computational machinery. That's to say, it is beyond the capacity of computational machinery to solve the problem reliably and accurately. And the way modern computer scientists have gotten around this negative result is to tell human beings not to give a damn about whether the problem is solved accurately, but instead to take whatever the computer says as the truth and to ignore reality. Anyway, we've reached a situation where we found at least one class of things that computers can't do, and that's reassuring. There's a whole world. This kind of liar paradox result, feed things to themselves with a twist, shows up all through mathematics and in particular in computer science to show that there's a bunch of things that there are limits to what's achievable. There's essentially what we're saying is there's no magic. And much though we might like to imagine the fun we would have if we could do magic, just remember the Sorcerer's Apprentice and remember all the terrible things that could happen if incompetent people could do magic. So we should be very much relieved by these negative results rather than disappointed. Anyhow, it's 5 to 10. I think we should take a little break. How about you?
What do you think?
Yeah. Shall I pause the recording?
Some nodding.
No. Good.
No
Right.
violent disagreement.
See you in 10.
Yeah.
Okay, folks. So we've seen one notion of computation, the Turing machine, and I thought by way of exploring computation a little further, we might spend the last hour of new material looking at another way of encoding computation that is altogether more fun. I suppose we should actually just do a little bit of admin first. So I've basically lined up the same people who cover your tutorials to be the humans who check over your checkboxes. And I'm hoping we're going to start that process today. If you haven't done your box checking, then please do. It's extremely helpful for us because the idea is that the people who are checking your marking don't actually have to do very much to confirm. It might make some small adjustments to your self-assessments. Some people are terribly down on themselves. Some people are inclined to claim credit that is not due to them. But by and large, the whole process goes a lot quicker, and goodness knows we need it to hurry up, don't we? If you just do your bit. But we'll be piling through that lot. Generally, we can go pretty quickly. I wish it was more automated than it currently is. That I have considerable incentive to use computation and machinery effectively to to alleviate the drudgery of running an assessment. But that's the situation. Next week is going to be pure revision, and I'm going to suggest, I'm not going to set a tutorial homework. I'm going to suggest that you look back through things you've worked on and struggled with and ask your tutors, direct your tutors to highlights of things where you're still scratching your head. Because the assessment will kick off in week 11. So that's not next week, that's the week after. And I'll give you at least 3 weeks to do it. I might need a bit of time to finish setting it. I'm gonna I'm going to finish the marking the old one before I set the new one. So I've got my work cut out next week. But that's the current state of play. So we're kind of at the if I'm not giving you tutorial homework on the contents of this lecture, then you should basically assume that this is just televisual entertainment. But what I wanted to look at was actually a notion of computation which is contemporary with Turing. And
Connor, let me point out one obvious thing, which is that even if you're given 3 weeks for the assessment, we don't expect you to need anywhere near 3 weeks to actually do it, right?
This is correct. However, I'm always aware of a couple of things. First of all, that people have complicated lives, and that offering people a larger window enables them to decide, which couple of hours they're going to spend on the assessment.
I just want to make sure no one is panicking that this is going to be a massive thing, right?
No, it's not going to be that much drudgery, but also the assessment is of online and open book. And this does create the possibility that some people may finally get their fingers out and engage with the teaching materials just in time. And that's what the 3 weeks are really for people to get it together to do the assessment. Because I'm not fussy about whether the message arrives sooner or later. I'm sufficiently desperate that I just want the message to arrive at all. Right. Shall we go to church? Yes. So, Alonzo Church, again, in the early part of the 20th century, cooked up a recipe for computation with rather fewer moving parts than the Turing machine. And it's a thing called the Lambda calculus. And in fact, the Lambda calculus is very much alive. It's what's doing the business inside Ask, apart from anything else. And you'll find that, as of version 8, Java has even caught up with the Lambda calculus. So this is the idea that that actually in practice took hold. Right. So let's start by writing the grammar of lambda terms. So there are, so there's, angle brackets and all that business, BNF terms. Yeah, are given by three different sorts of things. Well, and parentheses, I suppose. So yes, you could have a term in parentheses. Yes. You can have a variable. Yeah. You should, that's a variable should probably be some sort of non-terminal symbol labeled var, but we imagine that there are infinitely many strings available to use as variables. Okay. Then there is a kind of term built with a lambda and then a variable and then a dot and then a term. And this is a way of writing down a function. A function takes an input and delivers an output. And lambda variable dot term says we're going to use the variable to give a name to the input. And then we're going to say what term is the output given that input. So the variable that is to the left of the dot is probably going to show up somewhere in the term, at least in interesting functions, to explain how the output is computed from the input. Okay, so the lambda is how we make functions. And then there's one more production in the grammar, which is straightforwardly term, term. I think you need to push that up. Right. So there we are. This last production is called an application. And the term on the left represents a function. And the term on the right represents the input to the function. And the idea is that this thing will compute to the output. So an application represents, we hope, the output that you get when the function consumes the input. So this is the syntax for the lambda calculus, and at some point real soon we'll tell you how computation actually happens. But basically, the plan is that we will explain how to transform terms systematically so that when computation stops, you get a vaguely sensible answer. I should also say that you can see if the grammar allows you to write 3 terms in a row, and if you do that, you need to know how they are associated. Application is most certainly not an associative operation, not like adding. The thing on the left is the function. And just like in ask, or rather, ask is just like the lambda calculus, application by default groups to the left, or as Roger Hindley used to say, application associates to the left, rather as we all did in the 1960s. Yeah, so that basically means that if you see a bunch of terms in a row, the leftmost one is the function and the others are the inputs. And that's why we have parentheses in order to disambiguate. Okay, so this is the stuff of this is the stuff of computing. And the idea is that, well, the essence of computational progress is nothing more than substitution. Let's have an example.
Yeah, I was about to say, let's have something.
Yeah. So I guess we should write a really simple function like lambda x dot x.
Good start.
It's a good place to start. Right. So this says
Matches the grammar, right?
Sorry?
Yeah, go on.
Yeah, so here we haven't used parentheses yet, and we haven't used application, but we have used lambda and we have used a variable. So lambda x dot x creates a function by saying, let's call the input x, the output is x. That's to say, this is the function which exactly returns its input unchanged. Okay, so that's one example of a thing. I suppose we could write a slightly larger example, or even modify this example to make it bigger. You could write some parentheses around lambda x dot x. And then to the right of that, you could write the variable y, for example. Okay, so now we've got all the pieces of our grammar in play. And the key thing that you need in order to be able to do computation is to know how these terms evolve. So that the way computation happens in the lambda calculus is that terms compute to other terms. So there's a relationship, there's a relation computes to that that relates a term which is less computed to a term which is more computed. And it's often written, as Fred has done, by a wiggly arrow. And so that's computes to. And the key rule that makes all of computation happen in the lambda calculus is that when you have an application, so a function, then an input, where the function is given as a lambda, then you can compute the output of the function by substituting the input of the function for the variable left of the dot in the term to the right of the dot. So we're going to substitute y for x in x, and that gives y. So that's what we said that this is the function whose output is exactly its input. We fed it an input, and look at what's come out, exactly the input. We call lambda x dot x the identity function. Okay, so that's the basic step. We could write it out more generally, uh, just to say lambda x dot t for any term t applied to some s computes to t with s substituted for x. Okay, so this is known in the business as beta reduction. Don't quite know. Well, okay. There's we'll get on to alpha in a moment. Right. Uh, so this is the basic thing. So you learned, you know, actually a long time ago, a lot of what you learned to do in school mathematics was taking some sort of formula expressed in terms of variables and using it to do a calculation by substituting actual data for the variables and then simplifying. And what Alonzo Church is saying with the lambda calculus is actually, yes, that is all there is. So this is so what's weird about the lambda calculus is not that there is substitution of lambda is basically a thing that lets you write down formulae. And the beta reduction rule says, yes, you can substitute an actual input for a variable that stands for an input. And that's how computation makes progress. And what's astonishing is not that that's an idea, that that's a thing. What's astonishing is that that's the only thing.
So
That
there's
this,
basically four things there, right?
uh,
There's variables, making functions and application, and then this rule which says what happens if you apply a function to an argument, and that's all the rest.
yeah. Now, uh, one thing that you need to be a little bit careful about uh, is to make sure that we don't mess up uh, which variable does what job. So in particular, so let's have another example um, uh, where we have lambda x dot lambda y dot x. Right, and you should understand how to read this. We operate the convention that after lambda variable dot, as far to the right as makes grammatical sense, it lives is the term that's after the dot. So this whole term is lambda x dot blah, and the blah is lambda y dot x. You put the extra parentheses in just to be totally clear. That's what's going on there. And then let's put more parentheses around that whole thing. And then let's apply that whole thing to y. Okay, now you need to understand something that's crucial. There are two y's in this formula. There's the one that's sitting as the input to the whole function, and there's the one that is a variable in a lambda. And these y's do not mean the same thing. because the idea is that the variable in a lambda is locally naming the input for the sake of saying what the output is. And the actual name you choose should not be important as long as it's used consistently. So when we compute this reduction by computation, there's a danger that if we just substitute textually the outer y for the x that's under the inner y, we might accidentally what's called capture the y. So there's a risk if we do this blindly that we might think this computes to lambda y dot y, at which point we're saying that the y in the input, which might refer to goodness knows what in some broader context, stops meaning that and starts meaning the y that's representing the input of that inner lambda.
So maybe if we take a step back, if we just look at this function, then what do we expect this function to be doing? Well, it's taking an argument, let's call it x, then it's taking another argument, and then it's returning x, right? So it's taking a first argument, ignoring a second argument, and returning the first argument. But if we were to substitute y in for x, then what we will get will be the function that takes a y and returns y. That's not the same function, right? So something has gone wrong if we do this substitution naively, blindly like this. That's what we're trying to say.
Yes. So the way you avoid this problem is to use exactly the freedom that it doesn't matter what you actually call the input in a lambda, as long as you use it consistently. So, for example, we could decide not to call the input of the whole thing x. We could call it a instead. You could change the lambda x into lambda a. And then, yeah, and that's completely fine, as long as you change all the use sites of that x into a. Okay, and we can do the same thing with our inner function. We can change that y into a b or a y prime, up to you, Fred, as long as we change none of the use sites of that y into b.
But then if we do that renaming, there's no clash anymore, right?
Yes.
It's obvious that b is not the same as y. So now we can do the reduction.
Yes.
So I'm going to replace all of the x's with y, because that's what the beta rule says, right? It says to apply this function to y. I find all of the places where the input occurs here, and I substitute y for it. So I'm going to get lambda b goes to y, which now is what we expect. This is the function that takes an argument and ignores it and returns y, which is what we thought this function was to start with.
Yeah. So that's the key thing, is that you should make sure you use your freedom to rename the locally, we say, bound the inputs of functions to make sure that we never accidentally capture other uses of the same variable name that aren't supposed to mean the same thing. So you make sure you rename a part
That's what, yeah.
Yeah. So that's this freedom to rename variables is called alpha equivalence. So you can think of both of these things as equations, but beta reduction is directed. You know, there's the left-hand side is less computed than the right-hand side. And then alpha equivalence is a thing that that you use when you need to make sure computation stays ambiguous or stays unambiguous. Real computers, well, yeah, sometimes they do use names. There are all sorts of ways to avoid the problem that alpha equivalence is solving when we write this stuff down. Right. So we've seen what lambda terms are. We've seen the basic mechanism we use to compute them. But that doesn't really tell us how to get stuff done with the lambda calculus. So I suppose we should look at a little bit of how we encode things you're familiar with. Like, right, you're used to computing being done with bits. So what does a bit enable us to do? Bits let us tell two things apart. So the key idea of lambda calculus, as far as actually getting computation done is concerned, is to encode things by what they're for. So the idea of a bit is something which, given two things, allows you to choose one or the other. So let's do it. We're going to have we can write the function lambda f. Dot lambda t dot f. So this is in fact the function we just saw with different variables on the other page. This is the function which consumes first thing f and then thing 2 and produces as output things f. So this is choose the left thing. But we could also have lambda f dot lambda t dot t. And this is given two things, choose the right one. And this enables us to encode conditionals. We use these two things to represent our two bits. The top one is 0, and the bottom one is 1. Yes, O and I, as we've been calling them in ask. And then you simply use application to feed two inputs to a bit, and the bit will choose between them. So, if you feed in, OAB is equal to A, because when you substitute A for F and B for T in F, out comes A, and IAB equals B. So it's a fun game to play to see whether we can build build logical operators with these things. Right. So
So it maybe seemed like we couldn't do very much at all with these things, right? We only had 3 things. But now we've seen that we can at least do bits and everything to do with bits. So that's a start, right?
yeah. So let's see if we can implement not. So not is going to take an input. So there's some lambda x. And then if we're hoping that x is going to be either O or I. And if it isn't, we play our usual game of garbage in, garbage out. So we're assuming that x is either O or I. And we can use the trick we've just seen to say, well, we can use x to choose between 2 things. And if x is O, we want I. And if x is I, we want O. So lambda x dot xio should behave like not. And maybe we should try writing, I don't know. Yeah, so yes. So
not O. I mean, I'm just going to substitute in what not is. That's lambda x applied to I. O applied to O. Okay, then I have an application of a lambda to an O. So this is going to be O I O. Okay, it's a bit McDonald's, but that's O applied to 2 things. So I know that that's going to be the first thing, which is I. So indeed, the not of false was true, as I wanted. Right? And I guess I could, it's not very instructive to do the other one as well. It's going to be exactly the same.
yeah.
Flipped around.
Shall we do NAND?
Uh-huh.
So we get lambda x, lambda y, and then let's think about it. If x is false, then NAND should deliver true. So that's x, I. But otherwise, we care about what y is. So if x is true, then if y is false, we also give out I. But if y is also true, then we should give out O. So basically what we're saying is, we can pretty much write down truth tables with this encoding. And if we've got NAND, then we've got lots of things, because NAND is universal. So that's kind of cool. We can do bits, we can do the whole of Boolean logic. Hope you're beginning to see how this lets us do lots of computation. But we would like to move a little bit beyond bits, because call me old-fashioned, but it would be nice if there were things that behave like numbers. So can we play the same trick of representing things in lambda calculus by what use they are? So let's try it. What use is a number? Somebody gives you a number, what can you do with it? You know, we started the year thinking of numbers as these kind of just-in-time kebabs made with buds stuck together with sticks with a lemon on the end. And what you can do with a number is to work your way along the spuds until you get to the lemon. And you are indeed promised that you eventually get to the lemon. And every time you take a step, every time you pull a spud off the number, you do a thing, right? What numbers let you do is control repetition. So you can do the same action some number of times to something. So shall we write down that idea? Let's write down what 0 is. So that's we take a function f, lambda f, and we take an input, lambda x, and we do f 0 times to x. That just means we give x back untouched. Okay, now let's write down 1, which takes lambda f, lambda x, and it gives back f applied to x. So that's doing f once to x. Let's write down 2. Note the use of parentheses to say that the outer f's input is the inner f applied to x. So we're doing f to x and then another f to the output of that. Okay, so in the past, I've said mathematicians, especially those of us who work with computers, like to count 0, 1, 2. Why am I doing this? Let's see if we can write down successor. So that's going to take a number, and then it's going to give us back a number. And what is a number? It's some lambda f, lambda x. And we are assuming that n knows how to do something n times to something. So if you leave a little bit of a gap and do nfx, that's f done n times to x. And now all we have to do to take the successor of n is do f once more. So that's the successor operation.
And we can check that indeed 2 is the successor of 1 is the successor of 0, right? Because 2 is f applied to something, and that something is what 1 returns if you give it an f and an x, that's fx. So we seem to have done the same thing, at least for 0, 1, and 2.
Okay. So maybe if you can shove that up a bit, but keep it visible, maybe we can lose NAND. But let's write plus. Okay. We're going to take two numbers, maybe they're A and B, so, or you call them whatever you want. Lambda A, lambda B. Okay. Now, how did we do adding? We got two loads of spuds, each with a lemon on the end, and we took and we put an extra spud onto the right number for every spud in the left number. So that's to say, we want to put a spud on, we want to put a spud onto B for every spud in A. So that's to say, we want to do successor A times to B. So that's otherwise known as A suck B. Right. And this,
Yeah, sorry, go on.
I was going to say, this is the point at which we introduce the third equation, that lambda terms satisfy, which is simply to say that we can eliminate the lambda b and the b on the end. Yes, you might as well add it there. Lambda x tx is equal to t if x is not in t. And for some reason, we skip a bunch of Greek letters and call this eta reduction.
I'm going to call it, I wrote that as an equality. Sometimes it's
Yes.
directed one way or another, but it's not. I mean, some people like to direct it from here to here because it looks like a
Yeah.
simplification, right? So maybe I'll actually do this.
Yeah.
Reduction. This is eta. Right. So if we apply that here, then here we see we have an instance of this, right? We have lambda b, something applied to b. So we could just write this as lambda a applied to suck, and it would mean the same thing. Like,
yes. So that's
both of
basically,
these things are the function that takes a b and applies a suck to that b.
I'm conscious of time. So we should kind of tie things up neatly. It's clear that this machinery can do a whole lot of stuff. We've got the means to do arithmetic. We've got the means to represent arbitrarily large numbers. We've got the means to do logic. So it shouldn't be that surprising to learn that you can model the tape and transition rules and the execution of a Turing machine using just lambda terms. And likewise, you can see these lambda terms are just built from a fixed repertoire of symbols, right? We've got an alphabet from which to make variable names, and we've got, other bits and pieces of stuff, lambdas and dots and parentheses and things like that. So correspondingly, lambda terms are things that you could write down on the tape of a Turing machine. And you can imagine that it might be rather laborious, but it is nonetheless the case that you can build a Turing machine that will compute according to the rules of the lambda calculus. So correspondingly, Turing machines and lambda calculus are equivalent presentations of computation. Not pragmatically, but there ain't anything you can do with one that you can't do with the other. And we noticed that Turing machines can loop forever, so we better just finish by writing down a bad news lambda term. And that, bad things happen when you feed things to themselves. That's how we made things go wrong. So what do you see here? This is a function which feeds x to itself. And now we feed that thing to itself. And how does it compute? What does the beta rule say? Well,
So we take the x and we replace all the x's with the input, which is this thing, right? So that's going to be lambda x applied to x, applied to lambda x applied to x.
yes, draw some arrows from the x's on the left to their replacements.
So right, so saying this is coming from that x,
yeah,
this is coming from that x.
yes,
we are taken this thing and plugged it in for both of the x's. Okay, but then we're not done yet, right? Because we still have a function applied to an argument, so we better compute that. But it's the same thing again, right?
yes.
So we're just looping around forever trying to compute this thing.
Yes. As the French say, plus ça mange, plus c'est la même chose. So yes, there we are. We have spent 2 hours exploring general notions of computation. We got Turing machines, which are kind of fiddly mechanisms. You can kind of imagine how to build one. And you've got lambda calculus, which is kind of rather easier to express yourself with conceptually because it talks more explicitly about inputs and outputs. But it's the same stuff. It's computation. It can do an awful lot of good things. It can do an awful lot of bad things, but it can't do everything. Looks like a good place to stop.
Okay, thanks everyone for coming.
Stop the recording.